Hello, everybody. Good morning or good afternoon, depending on where you're joining us from. Welcome to this APA Insights webinar on the next generation modular CSP technology. So today we have three experts on this subject. So please, just make sure that you listen carefully and send your questions. We'll be answering them after all presentations are done. And well, as you have just heard, we are recording this session and we'll send you the video recording and the slides as well. So right, so I would like to each of the panelists to introduce themselves briefly, and I'll introduce them as I see them in the order I see them on my screen. So Bruce, please, if you could please briefly introduce yourself. And you're on mute, by the way, so please. There we go.
Yeah, hello everybody. I'm Bruce Anderson. I'm the founder and CEO of 247Solar. I'm sure there are a lot of my friends out there watching. Thank you.
Thank you very much, Bruce, and very welcome. And Jane, please, if you could introduce yourself next.
Sure. Hi, I'm Jim Krause, Chief Revenue Officer for Capstone Turbine Corporation, now Capstone Green Energy. Excited to be here and looking forward to hearing what Bruce and the other partners have to say as we try and move the 24/7 CSP technology into the marketplace.
Excellent. Thank you very much, Jim. And Rainer, please, if you could briefly introduce yourself.
Thank you. Hello, my name is Rainer Buck. I'm part of DLR, German Aerospace Center, and I'm working there at the Institute of Solar Research. I'm heading the Department of Solar High Temperature Technologies, and I'm happy to be participant here in the discussion round.
Thank you, Rainer. So, right, well, I'm happy to have all of you here, and thank you to everyone who is here with us in the audience as well. We'll now play a short video, and after the video, we'll start with the presentations. With Bruce will be the first one to present. So, yeah. Okay.
Well, that was a pretty fast video, huh?
That was extremely short. So thank you very much.
Well, is there any way to try it again? Can you play the complete one?
Yeah, we'll try again.
24/7 solar plants are a game-changing way to produce electricity that generate baseload clean power around the clock 24/7 in any weather at costs competitive with PV today and coal tomorrow at scale. These modular turnkey systems use factory-built components, most of which can be manufactured locally with few moving parts for low maintenance and rapid low-cost deployment. 24/7 solar plants use the world's lowest cost solar mirrors to drive a proprietary hot air-based Brayton cycle system that operates at atmospheric pressure and requires no steam, molten salts, or oils. They combine the world's highest temperature solar receiver, which heats air to 970 degrees centigrade, with the world's lowest cost storage, which stores up to 15 hours of the sun's energy as heat instead of electricity, plus the world's most versatile, reliable power generator to create a breakthrough third-generation CSP system that stabilizes grids by responding instantly to changing demand. 24/7 solar plants eliminate most disadvantages of conventional CSP, PV, wind, and traditional power, and offer unmatched benefits for project developers and grid operators. They can be deployed on uneven ground and configured as a single off-grid system of 400 kilowatts or as utility-scale farms of unlimited capacity. Short project cycles, lower O&M, and competitive margins mean attractive returns for investors. 24/7 Solar. The business opportunities are breathtaking.
Well, right. So we'll get started with the first presentation by Bruce. And actually, before you start, Bruce, I'd like to remind everybody, almost forgot of a tradition we have at ATA Insights. Let us know on the chat box where you're joining from. So today I'm actually joining from Berlin. So Bruce, over to you.
All right. Well, thank you again, everybody, for joining. I'm very excited to bring this to you. We've been working on this technology for quite some time with partners such as Capstone and the DLR and others. And our goal is to produce power 24 hours a day at the cost and price of PV. That's a ways away, but you'll see why we think we can get there. A little background on the company. We are originally a spinoff from MIT, and in fact, MIT owns part of us. U.S. Department of Energy provided us with considerable amount of development funding some years ago, and we've really had great collaboration from around the world during those development stages. We know about conventional CSP, and it's been underrated and under deployed. It's making good progress now. It's making a good comeback, but there are really other opportunities for getting 24/7 CSP, and that's to imagine, if you would, for just a minute, that we can take the best of PV, which is low cost, low risk, rapid deployment, and both small and large scale, and the best of CSP, which is, of course, that it's 24/7 operational and 24/7 dispatchable. And we can get rid of the worst of PV, which is sunshine only, it's not dispatchable, and the worst of PV, which is its cost, complexity, and long project cycles and financing and so on. And we can also add additional benefits. And one of those, I'll let you read these, but the thing that I'll not mention often enough, but which is very, very important, is that it provides a really larger commercial opportunity, because the smaller scales have so many, smaller scale, which we're going to show you today, have so many more applications that until you're in this business, you can't imagine. And part of the reason for those numerous potential applications is not only the smaller size and the ability to deploy CSP on a distributed basis, but also because it offers industrial grade waste heat, about 250 C. Now, why is modularization so important? The key is getting costs down. And if PV and wind have shown us anything, that it's factory production that gets costs down. You've got to put as much of the cost of a CSP system as possible in a factory to get those cost reductions. And also, of course, what modularization and standardization does is reduces the costs on the site to deploy it. So you've got speedy deployment, and that gives way to rapid cost reductions. That's key in energy. Energy competitiveness is based on cost, along with some of the other attributes you could bring to it, like zero carbon and so on. But cost is the principal driver. So we must get our costs down. Modularization is a key approach to getting costs down. As I said, it opens the huge markets. Our system is standardized. Every system's identical, 400 kilowatts, and we have a 5 megawatt system on the drawing board. Short time to power revenues. And what I mean by that is that, let's say you're deploying 10 megawatts with a modular system. The first module that you erect and connect to the grid, you're producing power. So you don't have to wait for the entire project to be deployed before you start generating revenues and value. And our system doesn't use any water, steam. We don't use molten salts. We don't use oils. And we have very few moving parts. We have a few dampers and a few blowers, and that's really it. Except, of course, that the Capstone turbine spins, and the Heliostats, of course, track the sky, the sun. It's also something that can be put together like wind farms or PV farms, off-grid, mini grids, distributed or utility scale. These are firmly dispatchable every hour of the year. One of the reasons for that is the redundancy. Each of our systems has 2 Capstone turbines. And when you have, again, so let's say a 10 megawatt system, you have 25 of these systems. And these turbines will produce power even when there's a problem with the solar side of the system. So you've got all that redundancy. And these systems don't need a backup power plant when one of those turbines goes down. It's its own backup system. So it's also low risk because most of this equipment is proven. There's nothing really exotic about this. The materials are relatively simple, operations simple. The environmental applications are really straightforward because it has very little impact on the environment. And again, there's waste heat for water purification, industrial steam, and so on and so forth. The first big technical breakthrough that was required was to heat, because we were using turbines, and air turbines require higher temperatures than steam turbines. Our turbine, the Capstone turbine, has a turbine inlet temperature between 920 and 940 degrees centigrade. And so we need to heat air to even a higher temperature by 10, 20 degrees because we put it through a heat exchanger. And I'm going to get back to that in a few minutes. But first, I'm going to let Reiner go. And Reiner's going to give us some background on the origins of the solar receiver and its fundamentals and its performance. And I'll just say, in contrast to what Reiner's going to show you, which is high pressure, we have ours is at ambient pressure. So Reiner, over to you, and I'll stop sharing.
Okay, thank you. Now, let me. Okay, hope you can see my screen now. I will give you now an overview over the work on the receiver side. We were happy to join 247Solar team, and we are mainly involved in the receiver design, supporting 247Solar there with the design and with the manufacturing also, and also with regard to some of the system aspects. Okay, so where did we come from? We can say that we have a very long expertise in volumetric air receivers, and this is the technology which is also used here in 247Solar technology. We have done a lot of developments with pressurized receivers, with non-pressurized receivers. We use different absorber structures like wire meshes up to temperatures of 800 centigrade, ceramic foams, and ceramic matrix structures up to temperatures of 1000 centigrades. And we have also some experience with quartz windows, both for pressurized applications and segmented quartz windows, which are capable to work without pressure. So one example which was developed together with other partners in the past is what you see here in this picture. And to explain to you, we have a pressure vessel. So this was a pressurized system. We have a pressure vessel which has an opening, an aperture, which is covered by a domed quartz window. And the dome geometry is necessary to withstand the high operating pressure. We were operating those systems up to pressures of 15 bar, which were state-of-the-art, are state-of-the-art in modern gas turbine systems. So this unit is placed at the focal spot of the solar tower system, and the radiation is entering through a secondary, which is not always necessary, but in some cases, and then the radiation enters through the apertures, is transmitted through the quartz window, and then hits the volumetric absorber structure, which also has a dome-like structure. We call this section here the inlet section because the air which comes from the gas turbine compressor and the recuperator, the air is then moving inwards to this wide volume, and part or very small part of the incident radiation is captured here, and then it enters the main section, which is the biggest part of the absorber structure, and the air is then passing through this porous structure, the volumetric absorber, and this structure is heated up by the concentrated radiation, and the air is heated to the required outlet temperature by convective heat transfer from the very porous absorber structure. It's then collected and is moving towards the exit duct. So this was the pressurized concept that we used in various approaches. What you see up here on the top section is an example of a system which used tubes, metallic tubes, with also a small gas turbine system. And in front, it's a little bit difficult to identify, but in front you have segmented quartz, windows quartz strips, which are placed one beside the other, and they help a lot to reduce the convective losses and the thermal radiation losses. So basically, these were the starting point that we were coming from. We had successful solar receiver tests with gas turbine cycles. One test was performed at the Plataforma Solar together with a helicopter engine and modified helicopter engine operating in the range of 230 kilowatt electric power output. We had successful operation using receiver temperatures up to 1000 centigrades. Now the next step after that was a project together with Abengoa and other partners. And at that time, we used a Solar Mercury 50 gas turbine with a power level of 4.5 megawatt, together with this type of receiver, pressurized volumetric receiver. This was used, and at that time, we were operating up to temperatures of 800 centigrades. All these tests were done in hybrid operation, so we had part of the energy from the energy collected from the sun, from the heliostat field. And we also added fuel to bring the temperature up to the required turbine inlet temperature at that time, because the combustors that were used at that time were not capable to accept the full high temperature inlet going up to 1000 centigrades, which, for example, in the case of the 230 kilowatt engine would have been suitable to do solar only operation. So starting on this, what was the evolution to 24/7 solar receiver concept? We were engaged in looking into different different modifications with 24/7 solar. And the issue was that they did not want to go for the pressurized volumetric receiver approach because of the safety issues with the domed window, which is quartz glass, a brittle material. And this domed window is under high pressure. So this is a little bit critical with respect to the safety. They did not want to go that way. And the other issue is that an active cooling system is required for the window sealing, because you have to make sure that you always have a very even sealing of the window in order to avoid stresses which would lead to this damage of the quartz window. So based on these regions, 24/7 Solar developed its own approach with an air receiver, a volumetric air receiver at ambient pressure. And the heating of the gas turbine cycle is then done by an air-to-air heat exchanger. The large window that is intended to be used there is, of course, sensitive to pressure load. So for this reason, an additional exhaust blower is used to control the near zero pressure difference over the window to keep the window in stable operating conditions. And then we use volumetric absorber structures, as we did in previous receiver designs, wire mesh at the inlet section, because there we operate at lower temperatures, and the high porosity silicon carbide foam at the outlet section. Just to give you an indication of the operating conditions, The receiver in a typical layout is installed at the height of something like 31 meter, tilted by, for example, 24 degrees. And it's operating at ambient pressure with an air inlet temperature of 650 centigrades. This is defined by the gas turbine cycle, the exit temperature of the recuperator. And it's designed for an air outlet temperature of 970 centigrade. And of course, the overall system has a fuel backup option, and it's also designed to operate with the thermal storage. And the way how it operates, remember the receiver is at ambient pressure. Then of course, when it goes down to the heat exchanger, which heats the inlet temperature, the inlet air to the turbine, you have additional pressure drop. Eventually, you can introduce also fuel here to heat up if there is not enough energy coming from the sun, from the receiver. And then the additional component is here, this exhaust blower, which helps, or which is controlling by some minor suction pressure that the receiver is always at ambient pressure. In case we have the operation of the thermal storage, we apply this blower here, which creates an additional mass flow, and in addition to the mass flow defined by the microturbines. And this additional mass flow gets the additional energy if the energy is available from the sun, and puts it into the thermal storage. And when there is no sun or not sufficient sun available, we can use and extract the energy from the thermal storage and use it for the gas turbine unit. Here are some images of some of the components. This is the quartz window, which is intended for operation with the receiver. It has a diameter of about 2 meters. So you see a person here standing beside of the first prototype of that unit. It's built from multiple parallel quartz tubes, which are cut in the axial direction. And the segments are not interconnected. They are put very closely together, so there is nearly no gap between them. But they can more or less move freely one against the other, which helps to prevent this stresses which appear if you have very large, inhomogeneously heated surfaces, structures. It is equipped with an anti-reflective coating, which helps to avoid the reflective losses which typically occur on quartz windows. And it's mounted, as you can see here, on both ends. We have ceramic structures which keep the quartz segments in place, but allowing for some flexibility and some movement to avoid stresses. The other important component is the ceramic foam absorber. It's built from silicon carbide foam absorber, and it has a porosity of 20 ppi, or pore size of 20 ppi, and an open porosity above 90%. That means the struts of these ceramic foams are very thin, and we have quite effective convective heat transfer in these structures. And in addition to that, we apply a mass flow distribution setup. That means at the backside, where the air is exiting at the non-irradiated side, we apply ceramic structures like this, where you see a hole pattern in the structure. And this hole pattern defines the mass flow distribution. So at those sections which we want to have more mass flow passing through the structures because they get more radiation. We have more holes allowing for more mass flow through these structures. And then those sections where we want to have lower mass flow because of lower irradiation, in these sections we have smaller or less holes. and the overall pressure difference between front and back side of these structures is always the same. So with the application of those structures at the exit side of the absorber structures, we can implement a specific mass flow distribution, which then matches the irradiation distribution on the absorber surface. Of course, since the system is in preparation, we do not have measurement results, but the predicted performance from our simulation models is given here. And this is based on a heliostat field layout using 205 heliostats, each with 16 square meters, located in a site at Daggett, California, just as an example. And the expected performance of the receiver is now that we have a solar flux at the aperture with something more than 3.1 megawatt. The flux at the absorber is then a little bit less than 3 megawatts. We have, of course, thermal losses. So the absorbed power of the receiver is predicted to be 2.5 megawatt. This is the design power level of the receiver. And this is also including a certain solar multiple to be able to charge the thermal storage during most times of the day. And the resulting receiver efficiency, the predicted receiver efficiency, is in the range of 85%, 86%. Doing this on the annual base, the annual performance, we have total predicted output from the receiver of 6 gigawatt, and the predicted receiver efficiency as an annual average is 82%. And with this, I conclude my presentation on the receiver side and give it back to Bruce.
Okay. Carlos, can I go ahead and share my screen again? I guess I can. There you go.
Yeah, please.
All right. Okay. So this is what Rainer was showing us. And we've got the inlet air from the turbine at about 650 coming in, going through the wire mesh here, and then through the outlet absorber there. And here it is on top of a tower. And I don't know if we mentioned this, Rainer, but Fraunhofer and DLR developed the ceramic
volumetric absorber.
Yeah, the volumetric absorber. And not only can this solar receiver power the our system, the 247 solar plant, but we can direct all of that high temperature heat to an industrial process rather than using any of it to produce electricity, or we can do a combination of the two. And that has a lot of applications, of course. We hope that in the future we can raise the outlet temperature and perhaps do thermal chemical processes of various kinds. And that's not a subject we know a lot about, but it's an aspiration. And then we got a second primary system to our 24/7 solar plant, and of course that's thermal storage. What you're looking at here is what in the industry for over 100 years, approaching 200, is called a copper stove or hot blast stove or hot blast furnace, used by the steel industry, glass, metal processing, operating at higher temperatures than we do, and operating at a much larger scale. So basically, we've shrinked a very proven technology. It has no moving parts. And what we do is take the air from the receiver during the day, pass it down through the top and inside our storage media. They could be small size ceramic pellets, for example, from Saint-Gobain. It can be sand even, it can be iron slag waste. Very versatile. Now we're coming to the other third major subsystem of our 247 solar plant. And this we regard as the most versatile and reliable power generator of its size. And if you're not familiar with turbines, think of jet engines. That's really the analogy here. To our knowledge, it's the first ever commercial turbine that's able to convert atmospheric pressure hot air. Now just think about that, atmospheric pressure to electricity, no combustion, no emissions. Also to our knowledge, it's the first ever commercial turbine able to burn 100% hydrogen. Capstone has come down a long way. I think you're up to 60% hydrogen, Jim, with your standard turbine. And also the standard turbine can burn some dirty flare gases. This one, because of the design flexibility of the combustor, can burn almost any dirty flare gas. It can also burn low-grade methane. And with that, I'm going to turn it over to Jim.
Thanks, Bruce. And yeah, just on the hydrogen front, we'll have our smaller turbine operating later this year in a first commercial project at 100% hydrogen, and then the 200 kilowatt turbine is on the roadmap to be developed at 100% hydrogen after the C65 is done. So I will share my screen here. Great. So real quick, Capstone is a public company founded in 1988, and we went into commercial operation about 10 years later. The first 10 years of our existence was spent developing the different pieces of the technology to have a commercially viable microturbine. Unlike a lot of the other smaller microturbines or small turbines that are out there, we're not a adapted APU or technology from another application. We are a ground up dedicated microturbine. We are the world leader in microturbines. We have about 112 patents around the technology. Bruce mentioned one moving part, air bearings, no lubricating oil, no coolant. That's one of our foundational technologies that enables us to do some of the things that others in the space can't do. We have manufacturing here in California with a remanufacturing facility in the UK. We have 60 plus full-time distributors and some additional OEM partners like 247 and over 60 million operating hours. So it's a very proven technology that 247 has chosen to use. Capstone thinks as a partner with our customers and our project developers. We want to have long-term relationships, and we also have been focused on cleaning the environment and reducing carbon footprint since our inception. And there's some data here about our carbon reduction and some of our financial savings for our customers. So we're very excited to take that to the next level with 247, where we don't have to have any combustion unless the customer chooses to, and that combustion through the 247 turbine that we've modified with 247 can be renewable energy. And again, lining with our stakeholders, our customers, ESG is important. It's important to Capstone and it's important to our customers. And I think that what it says about our business and what it says about your business is that we're here to not only make money for our shareholders and our customers, but also provide environmentally friendly solutions to move from where we are in the energy space to a sustainable, renewable future. Bruce, a lot of talk about microturbines. Capstone on Earth Day of this year, thank you, Bruce, changed our name from Capstone Turbine Corporation to Capstone Green Energy. For the last few years, we've been doing more and more projects where we're combining technologies and developing technologies to help with that transition from a fossil fuel foundation for energy to a renewable foundation. And we've got the relationship with 247, as well as some of the hydrogen work we're doing, and thermal energy storage, battery energy storage. All of these technologies combined give customers the choices that they need to transition more quickly from the current energy environment to a renewable environment. I think one of the things that was also part of the decision making for 247 in selecting Capstone as their turbine provider was our global footprint. So we've got turbines in 83 countries, all 7 continents. We kind of go where our customers go. So we will be there along with our distributors supporting the 24/7 projects from conception to installation to long-term maintenance on the turbines. Kind of gives you a little idea of where our, what our distributor network looks like. It's adds about 600 employees to the Capstone 130 or so employees, and provides us a very geographically diverse network to help support the deployment of these technologies. And then one of the things that is foundational for us and our customers and sort of ties into that long-term relationship is at the time of the purchase of the turbine, we'll fix the maintenance costs for up to 20 years. So we'll sign a long-term, we call it factory protection plan. It's a long-term service agreement that covers all of the planned maintenance and all of the unplanned maintenance for up to 20 years. So we become, we make money when you make money. When the turbine runs, you're making money and we're not spending money fixing it. And so it really aligns our interest, and it also gives us the kind of relationship that we like to have that helps to ensure that the turbine is operating at peak performance to reduce any downtime. And it's all available as a standard product. I think that was what I had, Bruce, and I'm looking forward to any Q&A at the end that I can help with.
All right.
Yeah.
All right. Thank you so much, Jim. I guess if you stop sharing, I'll start sharing again.
And to everybody in the audience, if you want to send your questions through, now it's a time. So yeah, over to you, Bruce.
Yeah, so just to summarize here about this amazing turbine, it does produce electricity without combustion. It integrates with other power equipment, for example, in a microgrid kind of combination. It's a very robust oil and gas grade industrial product. Very low maintenance, as Jim said, typically 4 to 8 hours a year. That's partly because of the air bearings and lack of fluids. Fluids aren't necessary. Very long life. And we've added an exterior. We've removed their combustor. We've added a high temperature heat exchanger. And then we've also added outside of the turbine package a backup inline duct combustor. So many of you are probably scratching your heads. How do you use ambient pressure hot air to drive a turbine? And like I like to say, it's not easy. We removed the combustor, but we've added a high temperature heat exchanger in series with the turbine's recuperator, the low temperature heat exchanger. So we can take hot air from any source, and by that we mean at least 850 C. Concentrated solar power, a thermal storage system like ours has, for example, and or even hot exhaust air, like from a thermal oxidizer or other industrial system process, and put it through this heat exchanger, which is heating the compressor air that's going first through the recuperator, the low temperature heat exchanger, and then through our high temperature heat exchanger. And by this time, it's reached the turbine inlet temperature and pressure. So this is the whole system. It shows you where the components are, with the receiver at the top, the turbine. In fact, there are two of them on the ground, and the thermal storage system next to it. Our heliostats, there are 7 or 8 really outstanding heliostats in the world that can readily produce these 1,000°C temperatures. It's the receiver that's the tricky part, where you have to take all that sunlight, turn it into first heat, and then turn that heat, transfer that heat over to a working fluid, which in turn does something useful. So the heliostats reflect their light up on top of the tower. The cooler air from below, from the thermal storage and from the turbine, rise through the whole system, are heated in the receiver, come down at that almost 1,000° temperature. Part of it blows through the storage system, and part of it goes directly to power the turbine. At night, the air flows in the opposite direction through the storage and back to the turbine. Well, we've taken the heat exchanger and the turbine, we've put them together to create what we call an all-night battery. So we're also in that sort of long duration storage battery market as well. We've integrated the storage, and in this case, it's a horizontal shipping container size unit with a turbine, the 200-kilowatt turbine, and we've added thermal resistance coils in that blue section there. We pass air through those when there's extra electricity on the grid that's up for the taking, and we use that heat to heat the thermal storage. And then at night, or when the wind's not blowing, we take that heat back out of the storage system and power the turbine. And typically, it's a 200-kilowatt, 1.8 megawatt-hour turbine, so it's nominally 9 hours. But depending on how you operate it, we can get longer durations. And it's also relatively inexpensive to add more storage to the same unit. The important thing about this battery, though, is that even when it's fully discharged, it can operate 24/7 because it burns fuel. And these batteries will last a very, very long time. And they can be deployed at larger scales too. So we've got these 3 technologies, the 2 products that I mentioned, and multiple applications. Our intention is to be the lowest cost supplier of carbon-free electricity and heat, which is also applied to desalination, which has to operate 24 hours a day. Any carbon capture technology is going to have to operate 24 hours a day. We can also deliver CHP, combined heating and power, to industry, using both electricity and heat for industrial facility. And I mentioned ultra heat, where we can use the heat directly for industrial process, microgrids, and this is really important. This is an example. All these really are examples of how modular technology can be has so many more applications than large scale. Cost is everything. I'm going to zip through this really quickly, and I apologize because we're running short of time. But these are our cost projections, and you can see how the solid curves for our system are approaching with mass production PV prices and combinations of PV plus batteries. And I won't go right now into the cost benefits of our battery. The interest in our technology is unbelievable, and we have activity all over the world. Our very first commercial scale 247 solar plant and our heat store all-night battery are being built today in Arizona, and it'll be operational early next year. But as you can see, we're in active sales discussions all over the world. Not shown is India. India has emerged as a very, very active location for us. So thank you, Fred, for your quote here on the right. I know Fred Morris is online here, and we're ready for questions. Thank you very much.
Thank you very much, Bruce, Jim, and Rainer, for your presentations. They're all very interesting, and well, we can see here that there are a number of questions. So whenever you're ready, Bruce, if you stop sharing, then we can go through them. So Craig Turchie says, many advantages to your modular approach. Can you provide estimated solar to heat efficiency and net turbine efficiency?
Yes, I sure can. First of all, these turbines from Capstone are as efficient as you can get in this field. Their electricity, their efficiency is measured by electricity divided by the energy required to make that electricity is about 33% under ISO conditions. The efficiency of a CSP system is measured very differently. Efficiency of CSP systems typically are measured on an annual basis. And it is the amount of electricity that's produced divided by the amount of sunlight energy that's hitting the heliostats over the course of a year. And typically for CSP systems, these annual efficiencies are in the range of 14 to 17, 18%. They may have gone up since I studied that percentage. DLR and Reiner's team estimated that ours would be around 21%. We don't know what the number is. We'll have that for you next year.
Thank you very much. Right, there is a question here going directly to the cost. So, I think it's difficult to offer, straight figures, but maybe you could give us our estimates on.
Yeah, definitely.
Estimate Bassam Dali asks, what is the best levelized cost of heat you can deliver at, say, 970 centigrades?
I'm reluctant to share LCOEs or even levelized cost of heat because there's so many extraneous factors that relate to it, like debt equity ratios, interest rates, term, and so on and so forth. But what I can say is that we are quoting cost today for our CSP system, the CapEx, that is not for let's say a 10 megawatt system, that is not much higher than the 700 megawatt CapEx at the Dubai plant that's being built. So we're at the top of our cost curve. We're going to be able to move down our cost curve quickly. The LCOE in Dubai for that 700 megawatt system is around 8 cents, call it 8 cents. And now there are systems, as we know, that are being developed at lower cost in China, in Chile. The bids in both locations are quite low by comparison with the Dubai costs. And today we cannot compete with those numbers. We need volume to get our costs down. But our target in the United States, high costs are 4 cents or less. And of course, elsewhere, for example, India, where their cost might be, a third to half, we're expecting much lower LCOEs.
Thank you, Bruce. And another question by Craig Turchie. It says, air is a convenient heat transfer fluid, but not very efficient. How do you minimize parasitic losses due to blowers and pressure drop through heat exchangers and storage?
There's little doubt that is the key disadvantage of our system, is the fact that we use air, and that, like you said, it doesn't have a lot of heat capacity. In fact, it doesn't have very much at all, and it requires the movement of large volumes of air in order to transfer the heat that's required. Unfortunately, fortunately or unfortunately, we engineers tend to go for efficiency above all else. Efficiency isn't the point. The point is the cost of power, right? And so a lot of people chase efficiency, but that's not what the customer buys. The customer buys power at a specific cost. Now, having said that, our parasitics are fairly high. they can be as much as 25% of the output of our system. And so we will deploy our systems almost always with photovoltaic fields, PV fields. And we'll use that electricity during the day to power our parasitics and improve the overall efficiency and lower and at the lowest cost possible for our power.
Thank you, Bruce. I don't know if Jim or Ryan would like to add anything. You're rather quiet. Or should we go to the next question?
Yeah. Go ahead. There are plenty of questions, I think.
Yeah, all right. So, okay, so yeah, there are definitely plenty of questions. And, you know, Juan Ignacio Burgaleta asks, what are the main risks you have identified with this technology, and when do you estimate that you'll have a commercial plant in operation?
We call the systems that we're building in Arizona commercial systems. They're commercial scale, but they're ready for commercial deployment, and we will break ground on commercial deployments in the middle of next year. The key risks, frankly, are associated with the high temperatures. Whenever you're operating at these high temperatures, you've got associated risks, whether it's in the receiver, the ductwork, or in the heat exchangers, and that's where we see the greatest risks. But even there, we have an outstanding engineering team. We've had great help from our global development partners, such as Reiner at DLR. Gotten a lot of help from Capstone. We've definitely addressed all the risks that we know of, and it's the ones that we don't know of that I can't tell you about.
Well,
the nature of the beast.
Right, that makes sense. So right, so there's a question here by Alejandro Pagano, and he asks whether your concept is similar to the one developed by ETH and Alstom. Does it also include a CPC? But I think, you know, even if you don't know these concepts, how is this concept different to other similar attempts at modular CSP plants out there?
Okay, I'm not very familiar with the concept of ETH and Alstom, which is indicated here. At the moment, the main difference to our previous designs is that it's a non-pressurized design, and this has some implications. For example, on the window design, we use this to maintain low convective losses at these high temperatures. Otherwise, efficiency would be significantly lower. With regard to the CPC, which you have seen in our other designs in the 247 Solar design, there is no secondary concentrator foreseen, because with a good heliostat field, we do not see the necessity to add a secondary concentrator, which then would, of course, add again to the complexity, because at these temperatures and the required concentration levels, you would definitely need additional water cooling then at the receiver side.
Thank you. Ryan, I don't know if anybody else would like to add to this answer? No? Okay. Yeah, John Brinkhurst asks if Capstone and DLR have installed bases in Africa. Any plans for Africa or any?
Jim, why don't you answer that for Capstone?
Sure. So we currently have an installed base of microturbines in traditional applications, and we're pursuing opportunities with 247 Solar in Africa, specifically North Africa. There's a number of opportunities there that we've been pursuing for an extended period of time with Bruce and the team. So Africa is a growing market for us, and one that we see really being able to take advantage of the 24/7 or the thermal energy storage combined with the simultaneous generation of electricity for customers.
Thank you, Jim. And one question of my own is that, well, we see that right now, I think we're going through a global energy crisis, and I think we can predict that lots of governments, like, well, South Africa has been doing for a while, will issue tenders that will require quick deployment. So, you know, one thing that springs to mind is that this concept could be deployed faster being modular. Is that the case? You know, what kind of deployment times would you have in mind for, and, you know, could you start building and providing energy in series, as it were, like on a modular fashion?
The intention is to begin generating power as soon as you've deployed and commissioned the first single module, and then each time you commission a module, you're adding to the total power output. The rate of deployment right now for a single system, once you've actually broken ground, gotten all the permitting and everything else, is going to be at least 8 months in the field outside the United States someplace. Probably quicker in the United States, but it's also going to vary depending on how far off grid that application is. When we get into very large projects, let's say 100 megawatts, we expect to be able to deploy these modules very, very quickly. You know, maybe 1 or 2 a week over the course of a year to get to 100 megawatts.
Thank you, Bruce. And Sergio Castillo asks, how can 24/7 solar technology help Chile produce green hydrogen? So,
well, we want to be the 24-hour-a-day zero carbon supplier to hydrogen electrolyzers. And there are some electrolyzers that also increase their efficiency by up to 20%, or their total output, with heat. And so that's another benefit of our system, is that it produces heat for the electrolysis process and increases the efficiencies, lowers the per kilogram cost of hydrogen. And Chile is a great place. You have some of the best sunshine in the world.
Yeah, it's true. That solar resources. Right, let's pick some of the questions here. I don't think we're going to be able to go through all of them, but, you know, most of them. Right, there is a question here by Javier Rodrigo Duarte, and he asks, the injectors and combustor liner for fossil fuel operation or backup, are they the same of the standard Capstone turbines?
Oh, no, not at all. We removed the standard turbine, and on the outside is an inline duct combustor. And as I mentioned earlier, lots of degrees of freedom. We'll use whatever injectors and nozzles are required for a particular fuel that the customer wants, whether it be a liquid fuel or gaseous fuel.
Thank you.
And I see a question about the Heliostats.
Please.
Let me answer that, because we were really delighted when we put out an RFQ for Heliostats recently. We reached out to 8 different suppliers all over the world. We got responses from 7. They're all unique and different. All of them could achieve that 1,000-degree temperature that we need. And there's a lot of competition. We intentionally, at the very beginning, when we first invented this concept, we intentionally stayed away from developing Heliostats. We think they require human ingenuity, and we didn't think we had a corner on that market. And we felt there was going to be a lot of competition. And we had our hands full, frankly, you know, developing the other parts of the system. So no, we buy them from third parties.
Thank you very much. And well, we are coming up to the end of the webinar, and to close, I'd like to ask each of you to share, you know, some thoughts that you may want the audience to leave with. So don't know who'd like to start.
Why don't I go last, Reiner and Jim?
I'm happy to jump in. Capstone is really anxious and excited to be working with Bruce. The first project being not too far from the factory will allow us to be there and help with the deployment of the first semi-commercial system, if that's what Bruce is calling it. I think that's a great way to describe it, and look forward. We have lots of capacity, so the more success Bruce has, the more volume we get, and we can help bring that cost curve down, which is going to be important to the growth and sustainability of the business. But we're a committed partner to the concept and to Bruce and the 247 team, and looking forward to seeing it grow. So thank you for having me join today. I really appreciate it.
Thank you, Jim.
Okay,
Right, please.
Yeah. DLR as a R&D institution, we had the chance to follow and support this development now over a certain time. And of course, as an R&D institution, as a researcher, we are very much interested to see this really in work, in operation, and especially also to see if the predicted performance really matches what we have predicted. In our case, of course, regarding the receiver, but of course, we also are very much interested to see this predicted cost reduction to happen with mass production, because it's clear CSP has to bring down cost even more to be a good competitor in the market compared to other renewable options.
Thank you very much, Reiner and Bruce.
So I want to say, of course, thanks to Jim and Reiner both. They've both been awesome partners, and we're looking forward to continuing to work with them. I would also invite everybody to reach out to me. And this is a reminder. There's my address, phone number, whatever. And we would, we're excited about this technology, and so is everybody else. So we could not wait to bring it to the world to reduce the world's carbon footprint.
Yeah. And well, we'll be sharing the slides and the recording as well. So you'll get Bruce's contact details there. And well, I'd like to thank all three of you, Bruce, Jim, Reiner, for being with us today, and sharing your insights, and also to everybody who is in the audience as well. So thank you for being with us today, and well, I look forward to seeing you here next time, and see what we have planned for you at atainsights.com. Thank you very much.
And thank you to Carlos, Balin, Andres, and all the ATA.
Yeah,
thank you.
Thanks.